Okay, so hello everyone. Welcome to our weekly seminar series. I think we can start now. So today we have Dr. Rashi Jain with us. She earlier worked with Professor Sarita Viz at IIST Trivandrum, and recently she has finished PhD from the University of Strasbourg. Okay. And her area of expertise includes optical NIR studies of globular clusters, both galactic as well as extragalactic. And she also works with a lot of different types of optical NIR instruments such as UVIT, onboard astrosat, Vista, and Muse VLT and all. So Rashi, welcome to our weekly seminar series at Aries. You can share the screen and you can start. I will send you a reminder around 4:15, that is 45 minutes from now. You please start your presentation. Maybe first you can share the screen because your screen is not shared anymore.
Yes, okay, thank you. I'll also start the video. Okay, so thank you so much, Vedani, for the introduction, and thank you for this opportunity for letting me present my work. So already Vedani has told about me, so I don't need to reiterate. So I'll start with my research interest. And as Vedai told, I have from the beginning of my research career, I have worked on globular clusters, both galactic and extragalactic, ranging from optical, infrared, and ultraviolet. But most of my time I was spent in data analysis of infrared. In today's presentation, I'm going to focus on some of the aspects of globular cluster science. The globular clusters could be used as science cases to understand stellar evolutionary stages, to understand subtle processes that takes place within the interiors of stars, and to assess our understanding of these processes, thereby comparing various stellar libraries that are used for modeling galaxy stellar populations. And in the last part of the presentation, I'm going to talk about extragalactic globular clusters in the context of their environment and the relationship between their color distributions and their environment. So this presentation is broadly divided into three parts. The first part, I'll introduce the globular clusters and one of the basic applications of globular cluster science in understanding different evolutionary stages of stars. And this stems from the fact that they are supposed to have simple stellar populations. So in this one, we're going to see how the horizontal branch stars of NGC 2808 show that the populations are not actually simple. In the second part of this presentation, I'm going to discuss a particular case of NGC 697 in the light of understanding atomic diffusion in stars, and also to compare the performance of theoretical libraries versus empirical spectral libraries. And in the last part of the presentation, we're going to look at globular cluster systems in the Virgo galaxy cluster using optical, infrared, and near UV data, and to see how the globular cluster color properties could be related to their environment. To begin with the introduction of globular clusters, mostly in the presentations start like that when we say the globular clusters are a collection of stars, and they are very densely packed with stars of all evolutionary stages. So that's where so when one looks at a globular cluster at any time, it seems like a snapshot of all the evolutionary stages of a star, and you can expect to see all sorts of stars in a globular cluster. And therefore, the HR diagram of a globular cluster is very typical for all sorts of clusters. So this stems from the way the globular clusters were formed. So they are believed that globular clusters were formed when a dense molecular cloud collapses hierarchically, and then all the stars they form from the same cloud at roughly the same time. So they share similar chemical compositions and similar ages. But not all of these objects survive as bound objects. So, and those that do survive as bound objects, they form globular clusters. So since they are formed at the same epoch and from the same molecular cloud, they're expected to have similar chemical composition and ages. For example, here we can see the color magnitude diagram using Gaia colors for 14 globular clusters having different metallicity. So the color coding represents the metallicity of the cluster. And the red ones are most metal rich, and the blue ones are the most metal poor clusters. And they form a very neat sequence of stars for a particular metallicity. So initially, when one looked at the color magnitude diagram of the globular cluster, it was evident that these are the population of simple stellar population. But with better instruments, when we took a closer look at the color magnitude diagrams of these clusters, we saw that most of the Milky Way globular clusters display very distinct sequences within one color magnitude diagram. So here we see the color magnitude diagram of only one cluster, NGC 2808, using SST colors, and we can see very fine and narrow sequences of stars that can be seen in main sequence and giant branches as well. So the concept of distinct stellar population or multiple stellar population was then observed in most of the Milky Way globular clusters. And the signatures of variation in helium abundances were also found in these distinct groups. And spectroscopic studies also showed that there exist very typical anti-correlations between light elements like sodium and oxygen, carbon and nitrogen, and magnesium and aluminum between these distinct groups, which were not seen in the field stars, but only in the stars of the globular clusters. So that led to the confirmation that these stars were not all formed at the same time, and the globular cluster does not necessarily contain only simple stellar population. So the suggested formation scenario for the origin of these distinct stellar population suggested that there could be a self-enrichment when the cluster was being formed. And this self-enrichment, there are multiple scenarios, like it could have been because of the ejecta from the AGB stars, or supernova feedback from the death of the massive stars that died very early on when the cluster was evolving, or winds from the fast rotating massive stars. But there is not one consensus on how this might have taken place, but it could have been either of these reasons or a combination of these reasons. But now we know that for sure that the populations of globular clusters are not simple. This could also be exhibited from the horizontal branch of stars of NGC 2808, and we worked on the UV data from the UVIT telescope during my master's thesis, and we looked at the horizontal branch of stars of NGC 2808. And NGC 2808 is one of the oldest globular clusters in the Milky Way, and it is known to have a very extended horizontal branch. But the interesting result was here that we found. So in this color magnitude diagram, we see that there are distinct densities of stars, and these are the hot stars over here. But here we expect only the red horizontal branch of stars, and they were divided into two distinct groups. So we found that there are even in the red horizontal branch of stars, there was a bifurcation between these two groups, and another student is now extending this study by trying to fit spectral energy distribution to multiband photometry of the RHB stars. So, moving on to the second part. The globular clusters are not only important from the point of view to understand the stellar evolutionary stages, but to also understand how the stellar population of a galaxy, the characteristic of a stellar population of galaxies. So to understand the galactic stellar population, people usually build models, and these models become from simple stellar population, which is combined with star formation histories and chemical evolution, and along with dust and attenuation. And when these models are combined together, one makes the SCD of a galaxy. And this diagram here displays the role of simple stellar population in the formation of SCDs for galactic studies. So, in the ingredient list of SCDs of galaxies, stellar libraries play a very important role. Stellar libraries are usually of two types: empirical, which are made from the real stars, and theoretical libraries that are made from synthetic libraries or theoretical libraries. And globular clusters are used to validate the the physics that goes into these libraries or to calibrate the empirical libraries. So in this part of the presentation, I will show you how to use globular cluster as a test case to test the comparison between the different stellar libraries and to understand various processes that goes on within the interior of stars using the case of NGC 6397. So in this particular study, we are focusing on atomic diffusion in stars. So there are multiple mixing processes that goes on the surface of the star, and convection being most prominent one. But atomic diffusion is another mixing processes which is known to have an impact on various properties of clusters, predicted properties of the clusters. So the models or the models that account for atomic diffusion in their stellar physics, when they are used to estimate the ages of a star clusters, they bring down the ages from 10 to 12% when one accounts for atomic diffusion, and as a result of which one expects the metallicity in turn of stars to be smaller, but this is in theory. So what atomic diffusion does actually, so when the star is in main sequence and convection is the main mixing process, the impact of atomic diffusion is not expected to be seen. But when the star leaves the main sequence, the convection stops when the star is in turn off, and then one expects to see the impact of atomic diffusion in the stars. It is then when because of atomic diffusion, the heavier metal sinks to the bottom of the convective envelope, and the overall metallicity of the surface of the star is expected to drop. And that's why if atomic diffusion was actually happening to the extent that we expect it to be, the metallicity at the turnoff would be lower than the metallicity at the main sequence. To understand it better, this is a model of a low mass main sequence star of very low metallicity in different stages of its evolution. So main sequence turnoff and giant branch. And the bubbled area shows the convective layer. So when the star is in main sequence and convection is taking place, there is no accumulation of any metal on the top, and the metallicity of the star is what the metallicity is. But when the star moves to the turnoff and convection is stopped, excuse me, because of atomic diffusion, the heavier metal sinks towards the bottom of the envelope, because of which the overall metallicity of the star, the gray bar here, the overall metallicity becomes smaller than the main sequence. But when the star moves to the giant branch and the convection takes place again, it's reinitiated, and everything is mixed back up. So there is no accumulation of any element on the top layer, and the metallicity increases back up. So this is expected from the theoretical studies. So in one of the studies, the authors used the Muse spectra of stars in NGC 697, medium resolution optical spectra, to see if they can, if they find impact of atomic diffusion in the spectra of the stars. So they performed the full spectral fitting for the stars using a theoretical library called Göttingen Spectral Library, and derived the metallicity, temperature, effective temperature of the stars. And what they found is displayed in this HR diagram. So this HR diagram shows the luminosity on the y-axis and effective temperature of the stars on the x-axis. And the stars are colored according to their derived metallicities using the theoretical library. So if you see the average metallicity in the main sequence and turnoff and giant branch, what we observe here is that the metallicity at turnoff is lower than the metallicity at main sequence, and then as we go towards the giant branch, the metallicity increases back up. If we look at the average values, the metallicity at the turnoff, the value of the metallicity is minus 2.1 dec, and the metallicity at giant branch, the average metallicity is minus 1.9 dec, which means the changes predicted by the author is around 0.2 dec. Now, I'd like you to look at what the library that they have used in their study. So in the first panel, the gray dots here are the stars of the globular clusters in the parameter space. Metallicity versus temperature on the bottom panel, and the surface gravity versus temperature on the top panel. And the black dots are the library stars. So since it is a synthetic library, it is uniformly spaced in parameter space, and the stars are computed at intervals of temperature and metallicity. So the metallicity in the metallicity range of the globular cluster, it's minus 1.31. We see that the stars in the library have a step of 0.5 dec, and the impact and the difference between the metallicity of turn-off and Jain branch is 0.2 dec, which is smaller than the step size, minimum step size of the stars in their library, which casts a suspicion about the impact that was seen in their results. So in our study, we repeated the same study, but instead of using a theoretical library, we used two popular empirical libraries. So in our study, we have used LOD, and the stars here are the LOD stars, and we have only used the stars that satisfy the temperature and metallicity range of the stars in the cluster, and the third library, Millis. So we performed the full spectral fitting of the stars using these two libraries and derived the effective temperature and metallicity of these stars. So in our study, we'll only focus on the stars from the turn-off to the Jain branch, because we want to see the trend from turn-off to Jain. Also because the stars in the main sequence have signal-to-noise ratio of less than 20. So we only want stars to have good signal-to-noise ratio to see what the trends are. So, okay. And on this panel here, we only see the metallicity values versus effective temperature for turn-off to the Jain branch. For the first panel shows for the theoretical library, GSL, and the bottom two panels shows for LOD and Millis respectively. So here we see that what we have seen, that the metallicity increases from the turn-off to the Jain branch when they used theoretical library. But with in our study with LOD, we find basically a flat trend. So there is no trend. The metallicity does not change a lot. But with Millis, we find a trend that goes first the metallicity drops and then increases slightly. So the three trends are entirely different, and they are not consistent amongst each other. And the amplitude of trend seen, so the red bars here are the standard deviation, and the standard error will be divided by root n, so it will be even smaller. So the amplitude of trend is higher than the standard error. That means the trends are significant. So that means the libraries show inconsistent results, and there is some kind of inconsistency either in the way the libraries are computed or the way the interpolators are being used. So a follow-up study was done using different interpolators on another theoretical library. And what they found was, if they use another theoretical library, they found a similar trend. The metallicity increases, but the interpolators have no impact on the results. So this is still an open question, that what is inconsistent between these libraries that give rise to these differences, because these libraries are very widely used by the community to study the galactic stellar populations and also the stellar evolutionary stages. So we have the two kind of libraries that have their own pros and cons. For example, theoretical libraries, the coverage is not limited. We can produce the stars in the parameter space for any temperature or metallicity that we want, but they are influenced by the systematics and are limited by our own understanding of stellar evolution and also our computational capabilities. Whereas empirical libraries are based on real stars. So they have real stars, and we can trust the physics. But then they are characterized using theoretical models themselves, and they are limited in wavelength range because we observe the stars that we observe in nature, and they are limited in parameter space. And the problem of observing metal poor stars still exists. They still remain difficult to observe because they are very faint, and with the instruments that we have, we still don't have as many metal poor stars as we would want. So we also saw that atomic diffusion, the processes like atomic diffusion, which are important to, we know that the ages of globular clusters could be brought down to reasonable estimates only when one accounts for atomic diffusion, but we still don't know to what degree atomic diffusion happens on the surface of stars. But to do so, we still have certain limitations, but they're not in terms of the interpolators that we have, but there are inconsistencies that exist between theoretical and empirical libraries amongst themselves. And there is more work which is needed to make these libraries more consistent and more complete, especially in the metal poor regime. And one such library that is going to add more stars in the metal poor regime is the X-shooter spectral library, and the work is still going on. Moving on to the third part, I'll take you to globular clusters in the Virgo galaxy cluster to see the subtle relationship between their color distribution and their environment. When I say environment, I mean where the clusters are. Are they close to a massive galaxy? Are they a part of a lenticular galaxy? Are they intracluster globular clusters? And does the environment or local condition impact their color distribution? So the motivation for this study came from another previous study, which was based on globular clusters around M87. M87 is a massive elliptical galaxy, and it sits at the center of Virgo galaxy cluster. You might remember it from the galaxy that hosts the black hole, the image of which we saw a couple of years ago. So M87 is a massive elliptical galaxy, and it's known to have around 13,500 clusters at least. So the authors observed the globular clusters around M87 in a field of around 1 degree by 1 degree, and they classified these clusters based on their location with respect to the central galaxy. So they classified these clusters into 4 groups: the central cluster, which are very close to the galaxy; the clusters which are in the outskirts of the galaxy; then clusters that belong to other galaxies, other spiral and lenticular galaxies in the field here, the magenta data points, and then the intracluster globular clusters. And then they studied their color distributions based on their environment. So the colors correspond to where these clusters are, and they're compared with the locus of the same color distribution for Milky Way, the black locus here for 12 Milky Way clusters, and then with theoretical models from Roussel and Charlot. So these are just for guiding the eye, and one can notice that they become shallower as one moves away from the center of the galaxy. And the intracluster globular clusters are the one which matches the locus of the Milky Way the closest. Now, what this means is if the color distribution depends on the environment, that means the clusters differ in their spectral energy distribution. And because these clusters are what are used as reference objects to test our models for their integrated properties, it's important for us to know if there is difference when one uses clusters from center of the galaxy or from away from the galaxy. So since this is just one field, we needed to extend this to a broader field or to different fields to see if this is a general phenomena or was this just particular field which is a special. So, excuse me. So in this study, in this panel, we see the Virgo cluster, and in this study, we have extended this similar kind of study to another part of the field. And the part that we saw was around M87 here, and then we extended it to another galaxy, M49, which is the brightest galaxy in Virgo, and in the region between these two galaxies to see the intra-cluster globular clusters. Why do we choose Virgo galaxy cluster? The first reason is because it's the closest to us, and with the facilities, with the observing facilities that we have, the globular cluster at the distance of Virgo are marginally resolved, so that makes it convenient. Then it has a dense concentration of matter, so it has different kind of galaxies, but mostly relatively young galaxies, a larger fraction of spiral galaxies than elliptical, but we have different morphological galaxies. So this makes it a very ideal site to go and hunt for globular cluster in different environments. And in this study, we have used the data from Next Generation Virgo Cluster Survey, which is a survey that covers 104 square degrees from the center of the around the center of the cluster. and it extends the optical data in 5 bands, U, G, R, I, and Z, and it is complemented in the infrared by NGVS IR in J and K band, but it only covers a part of the field, which is shown here. So the red part of the field, which is already studied around M87, and the black part of the field is what is reduced and analyzed in this work. Here is the field around M49. At the center of this field is M49, and this region is where the intracluster globular clusters are studied. So this is just technical detail what the detector, so the detector of the Vista telescope looks like, and maybe I can just skip the slide technical part and this is okay, data reduction. So we have used infrared data in JNK band. So we received the pre-processed images from Cambridge Astronomy Survey Unit, and these are initially subtracted for sky and other artifacts because of observation. And we received the images which look something like this. So they have the gaps in between. And we use these images to first create an object mask to mask the bright objects. And then after we mask these objects, we estimate the sky and subtract this sky. Apart from sky subtraction, we also do another pass of subtraction for some artifacts which are left behind because of systematics and other instruments. And after which we perform another pass of astrometry and then stack these images. And we get a stacked image like this for the entire field. To make to make the detection of globular cluster around the central galaxy easier, we also subtract galaxy and then we perform photometry. Then there are some other steps that have for improved calibration, and the end product as an end product we get a stacked images and also the catalog of the objects. So this is the image. I mean, I said that the images that we get are pre-processed, so they are already subtracted for the sky. But there are still some small level patches and patterns that we can see in this image, which are improved and becomes much more flat. The background becomes much more flat after we perform our sky subtraction. And to give you an idea how big the image is, so this image, the bottom part of the field, it covers around 3.5 degrees on this axis, which is on physical scale 1 megaparsec. And this galaxy here is M49. So how do we select globular clusters from the swarm of objects, the foreground stars and the background galaxies? So here we use the magic of multiband data that spans from UV to optical to infrared, and then we combine these 3 bands to get the spectral information for the objects. And this results in what we call is a UIKS diagram, which is an exceptional tool to diagnose the compact stellar objects like globular clusters and ultra compact dwarfs, which are marginally resolved. So yes, like I said, it combines the photometry from near UV, optical, and near infrared. Then we also have something which is called compactness index. And compactness index is basically a size parameter, and it's the difference between aperture magnitude for the object in a bigger aperture and a smaller aperture. Now, since these aperture corrections are derived using stars, for stars this difference will be 0. But as the objects become larger and larger, this difference becomes more and more positive. So like in this diagram, we see the star, this is the stellar sequence, and it has the typical values of 0 of compactness index. Whereas this object, this island over here, the green one, is where the compact stellar systems are, globular clusters and UCDs, which are not very large, but not, but since they are not stars, they have a slightly higher than 0 positive values. And then this blob here is where the galaxies are, the star forming galaxies and the elliptical galaxies. And when we combine the compactness index with the colors, we get a modified UIKS diagram, which makes the this is a color diagram, and this is a modified UIKS diagram. So the difference, so the separation becomes even more neat, which facilitates selection of objects. So to select globular clusters in this color diagram, we have used density-based classifying algorithm. So in this case, we have used two-dimensional Gaussian mixture model, and we have applied it to the modified UIKS diagram. But we only use objects that have photometric error in all the ones less than 6%. There are two reasons for that. First reason is because it makes the selection much more easier, noise-free and easier. And the second reason is the sort of effect that we are behind or we are looking at are very subtle. And since they are very subtle and of very small order, we want only the best photometric objects in our sample. So the blue objects here are our globular cluster sample that we have selected. But this sample still contains contaminants. So there are high chances of having stars and galaxies in this sample of objects. So we use another criteria of rejection. To reject the stars, we look at the luminosity function, and from the luminosity function, from the peak of the luminosity function of globular clusters, we know that we do not expect to see any globular clusters which are brighter than 18 magnitudes. And here is a clear bimodality, and anything which is brighter than 18 magnitude is not a globular cluster, so we reject all those objects. And then we reject anything that has an IC larger than 0.3. So we reject the extended objects as well. And here we can see how neatly this separates globular clusters from everything else. So the gray dots are the initial sample that we selected. And after rejection, what is left behind is the blue, which is clustered around the major galaxies in the field. So here's M49, and then there are other two big galaxies. Now, after we have selected our globular cluster sample, we will look at the color-color relations of these globular clusters. This shows the globular clusters in the entire field of study, the bottom field that has M49 and other two galaxies, a lenticular galaxy and an elliptical galaxy. And the top part of the field where there are two major elliptical galaxies, and the rest of the globular clusters mostly belong to the intracluster globular clusters. This is about the completeness and contamination of the sample. I'll skip this part, but if you're interested, you can ask the questions about it later. Okay. About the results. So first, the globular cluster, the globular clusters that we have selected, we want to see if their properties are consistent with what is expected from the globular clusters in galaxies. It is known that the globular clusters in most of the massive galaxies show a color bimodality, and they are divided into red and blue subset of globular clusters. And the red globular clusters, the formation of red globular clusters is expected to have happened within the galaxy itself or in situ, whereas the blue or metal poor globular clusters are expected to have been accreted from satellite galaxies or the intracluster part. So since the formation of these two sub populations of the cluster is distinct, we also expect them to have distinct properties. For example, their sizes, their distributions, etc. So in this diagram, we have displayed the colors on the x-axis of the clusters around M49 and their size on the y-axis, and they're colored by their distance from the central galaxy. And the blue globular clusters are on average more extended as compared to the red globular clusters, and red globular clusters are also more concentrated around the center of the galaxy, whereas the blue ones are more extended. So if the scenario of accretion is true, then one expects the blue globular clusters to be more distributed around the galaxies, whereas the red clusters should be more concentrated around the center of the galaxy, which seems consistent. And because of the tidal forces, which are very strong near the center of the galaxy, the red globular clusters usually have a ripped off envelope, are expected to have ripped off envelopes, so smaller sizes as compared to the blue globular cluster, which also seems consistent. So these properties are consistent, and they hint at how a galaxy might have formed or evolved during the course of its evolution. So we'll look at one set of globular clusters and their color distribution. This is the distribution, this is the spatial distribution of these clusters and different groups. So M49 is a massive elliptical galaxy, and then there is a small elliptical galaxy and another lenticular galaxy. So we have divided it into four groups. The central globular clusters of M49, then outskirts of M49, lenticular and elliptical galaxies. So we have done a maximum likelihood fit for the distribution, the color distribution, and the hatched area shows the 2 sigma or 95% confidence interval of the fits. And on the histogram panel, we see the color distribution of the respective colors, and they are consistent with what one expects to have the galaxies of. So, for example, the elliptical galaxies here. The red part, the central clusters are bimodal, so it has a red part and a blue part, whereas the outskirts shows mostly blue globular clusters around M49 and so on. So there are we had like seven bands, seven optical bands, so we can have more than 100 combination of colors, but we selected only a few just to show what kind of trends one can expect. So not all of them, but a few trends are more significant at 2 sigma level, and the trends of S0, so S0, the lenticular galaxy, and the elliptical galaxy, the green and magenta, shows the most distinct patterns as compared to each other. In the central M49 clusters and the clusters of the lenticular galaxies show similar trends, whereas the outer M49 show resemblance to the elliptical globular clusters. Now we look at the intracluster globular clusters as compared to the elliptical galaxies in the field. So the intercluster, the sign, the sign locus shows globular clusters of M86 and M84, which are ellipticals, and the orange locus shows the intracluster globular cluster. And similar to the previous one, there are certain bands, especially the ones that involve I and Z, that show most distinct, the distinction most strongly. And intercluster globular clusters shows more distinction as compared to the other elliptical galaxy globular clusters. To summarize this part of the presentation, we looked at the globular clusters in different environments, and we looked at their color distribution, that means the spectral energy distribution versus environment. So in some of the color combinations, the differences are larger than 2 sigma confidence intervals, and there are no major disagreements with the trends which were seen for the globular clusters for the globular cluster of M87. One can see that these differences become more prominent when one uses the bands, the colors in I, Z, and K bands. Now, since we are trying to connect the differences in the color distribution or spectral energy distribution with respect to their environments, the possible explanation could include the differences in age and metallicity, because they are from different environments. They are going to have different metallicities and different ages. But they could also be linked to the surface chemistry of the stars that traces the chemistry of their environment, and also the multiple stellar populations could be one of the reasons that could explain, that could be one of the factors that could lead to the differences in SEDs. All the local conditions that are also known to affect the initial mass functions could also be one of the factors. To conclude the entire presentation, so in the first part of the presentation, we looked at the multiple stellar populations in globular clusters. Then we saw how globular clusters are important from the point of view of understanding the subtle mixing processes that goes on in the stars, for example, atomic diffusion, which also affects the age estimates of globular clusters. But the mixing in the stars is so far not very well constrained, and we do not know yet very precisely what is the amplitude of these processes that takes place, and it still remains difficult to quantify. Some of the high resolution spectroscopic studies have tried to look at elemental lines to see if they find any traces of atomic diffusion. Very few of the studies have confirmed that they have found signatures of atomic diffusion, but majority of the study do not see any traces of diffusion. So this calls for improvement in the libraries as well, because we know that our libraries are not complete. The empirical libraries are not complete, and theoretical and empirical libraries are not very consistent among each other. In the next part of the presentation, we looked at the globular cluster color differences, which are very subtle when looked photometrically, and they're likely to have environmental origin. The origin of these differences could be attributed to nature, for example, the initial mass function, or nurture, the interaction of galaxies, or no interaction. But the importance of infrared data for selection of globular clusters and understanding or study of these differences is very important. But we need precision photometry with deeper and more broad coverage in different fields to confirm to confirm these trends if they are seen, and to explain the origin of these differences. So the work towards completion and consistency of stellar libraries is going on. People are working on making these libraries more consistent in wavelength range. So UV, infrared, and optical all work together, and also the different libraries consistent among each other. And in terms of infrared observation, we know that we are going to see a lot of new telescopes and surveys in the next decade. That includes Euclid, which is going to cover around 15,000 square degrees, but we will have similar, it won't be very deep, but it will cover a very broad sky. And Roman Space Telescope, which will have amazing resolution, and it will be very deep. So, but it has pointed observation, but we'll still have more fields to look at. And with AWST, we also expect to see protoclusters forming. So the future of extragalactic globular clusters look really exciting. And thank you for your attention. If you have any questions, I'd be glad to answer them.
Thank you, Rashi, for a very nice presentation and finishing it in time. So now we have ample time for discussion, question, comments, feedback. So I encourage people from audience to unmute themselves and ask the question, or maybe raise the question, raise your hand, and I will unmute them. Please go ahead. Yes, Brajesh, please go ahead.
Yeah, Rashi, it's a very rich data you have presented. I'm Brajesh here.
Yes,
so particularly this globular cluster population and their formation, as I could see that you have worked on a huge amount of infrared data. Yes. On color distribution of globular clusters and galaxies. So as I recall that these information were known, I mean, blue globular clusters and red globular clusters are two bimodal populations. And people have also studied the kinematics. Yes. I mean, just to support two modes of formation episodes in that particular galaxy by whatever means. So, so would you, in this slide, would you comment? I mean, I just was curious to know what this infrared data, whether are you getting some third population kind of thing, or in what way it could be helpful in reflecting on the formation scenario for these globular clusters, which has been long outstanding since long, right?
The importance of infrared data, you're right about the fact that people already know that the bimodal distribution of colors exists, and these properties are distinct, the dynamics and the kinematics. But the importance of infrared data is the first thing is the selection, like the UIKS diagram, because people have initially worked with BZNK and other combinations, but the distinction was not as clear as in UIKS diagram. And that's why the infrared data, that's where the infrared data comes into picture to select if we want to study globular clusters at the distance of Virgo. And so there are other clusters like Fornax cluster and Coma cluster, which are even farther away. So it won't be possible for us to identify globular clusters with confidence if we do not have infrared data. So the first thing is infrared data is important to identify globular cluster and to separate them from stellar sequence and from background galaxies. Then with JWST, if one wants to look farther away in the universe, I think infrared data will be very valuable because the farther we go, the objects become more and more bright in infrared. So I think that's where the importance of infrared data comes into picture.
Okay, okay. In one of your M87 global cluster distribution, I could see that there is some trend. Would you please explain that?
Do you mean the color diagram?
Yeah, here in this one,
yes.
you can see that the red one,
yes.
they are sitting almost isotropically, right? I mean, symmetric to the galaxy center. But the probably orange ones, they have a certain tendency. Could you look into this?
No. I do. I don't understand. Isotropic to the Milky Way globular cluster. Do you mean?
No, M87. M87.
Yeah.
I mean, this
yes.
is
okay.
So the red ones.
Mm-hmm.
Red ones are pretty close to M87 galaxy clusters.
Yes.
But the orange one, do they belong to M87 or they belong to Virgo cluster?
They actually, okay, so you're right about it because we did not do any kinematic selection because the radial velocities for all the clusters are not available, and this selection is only based on the proximity to the galaxy. So it's possible that the orange globular cluster group also has intracluster globular clusters within the sample, but majority of the clusters belong to M87.
Oh, you mean the orange one as well?
Yes, yes.
Yeah, but the kinematics will tell truly whether they belong
yes,
to or not.
Yes.
Okay. Okay. Thank you.
Thank you.
Okay. Any more question from the audience? If there are none, so let us thank the speaker once again. So thank you, Rashi, please, for joining and showing your research work. It's a nice work. Okay, and then so everyone have a nice evening, and we will see you next time. Bye bye, and enjoy the evening. Okay,
thank you.
bye.
Bye.